who will deliver the lecture on topic metal complexes in therapeutics. This lecture will introduce us to promising role of coordination compounds in medicinal chemistry and their mechanism in therapeutic applications.
Thanks, Tanya. Good afternoon, everyone. Myself, Hina, working under supervision of Professor Gurjaspreet Singh. Today, my topic of presentation is metal complexes in therapeutics. So, in the first section, we will discuss about iron. It is a small metal in first transition series in periodic table and has a atomic number 26. It is represented by symbol Fe, which is derived from Latin word ferrum, which is related to its firmness. It is by mass the most common element on Earth, forming much of Earth's outer and inner core. It is the fourth most common element on Earth crust. Then we need to know what does iron do in our body. The iron that we take through food in +3 oxidation state is absorbed in +2 oxidation state in mucosal lining and stored here temporarily as a ferritin complex. From there, it is transferred to various body parts through transferrin, where it may be utilized for synthesis of hemoglobin and myoglobin in RBC and bone marrow respectively. The leftover iron may be stored in macrophages and liver as ferritin complex. So about 70% of iron in body is found in hemoglobin and myoglobin. A large number of enzymes require iron as a cofactor for their functions, as the enzyme involved in oxidative phosphorylation, the metabolic pathway that convert nutrient to energy. Then we need to know what are different functions of iron in our body. Iron support our healthy growth and development. It helps to deliver oxygen to various parts of body. It helps to maintain our energy level and keep the level of oxygen in our muscles. There are two types of iron that is present in food, that is heme iron and the non-heme iron. Heme iron found in red meat, poultry, pork, and it is the most easily absorbable form of iron. The non-heme iron is not as easily absorbed by our body as compared to heme iron, and it includes breakfast cereals fortified by iron, bread, pasta, tofu, bean, dried fruit, and egg. Eating food which enriched with vitamin C, such as tomato, citrus fruit, bell pepper, can also help in the absorption of iron. Then we need to know when are different stages of life where we need to pay extra attention to iron intake. So during infancy and childhood, during adolescence, from the onset of menstruation to menopause, and during pregnancy, also when our diet do not include animal product. Then we will discuss what happens if we don't get enough iron. So when level of iron stored in our body become low, iron deficiency anemia sets in. RBC becomes smaller in size and contain less hemoglobin, as a result of which blood carries less oxygen from lungs throughout the body. The symptoms include iron deficient anemia, including gastrointestinal upset, weakness, tiredness, lack of energy, problems with concentration and memory. Infant and children with iron deficient anemia might develop learning difficulties also. Then we will discuss different stages of life, the effect of iron deficiency. So in pregnant women, during pregnancy, as the amount of blood in women blood increases, so she needs more iron for herself as well as her growing baby. So getting too little iron during pregnancy increase women risk of iron deficiency, and her infant risk of low birth weight, premature birth, and low level of iron. So anemia affect on an average 24% of pregnancies and can cause more than just tiredness to the woman and her growing baby. So it can impact body development of baby. It can slow down the post-delivery recovery, and it can also increase the risk of requiring a blood transfusion. In infants and toddlers, iron deficient anemia can lead to delayed psychological development, social withdrawal, and less ability to pay attention what is happening in their surrounding. By age of 6 to 9 months, full-term infants could become iron deficient unless they eat iron enriched solid food and drink iron fortified formulas. So iron supplementation is very necessary for infants as it prevents anemia, it improves neurodevelopment in iron deficient infant, and it alters metabolism of trace minerals. As we discussed, iron is very important for our body. Also, its excess can cause harmful effects. High dose of iron supplements, especially on empty stomach, can cause an upset of stomach, constipation, nausea, abdominal pain, vomiting, and diarrhea. A large amount of iron may also cause more serious effects, including inflammation of stomach lining and ulcers. High dose of iron can also decrease zinc absorption in our body. Extremely high dose of iron in 100 or 1000 of milligram can cause organ failure, coma, convulsion, and even death. Hemochromatosis is also a disease that is related with excess of iron, and it involves iron absorption and storage in organ like liver, heart, pancreas, leading to potential organ damage. So the health hazards that are related with excess of iron include the amplification of Fenton reaction, which produces reactive oxygen species. The reactive oxygen species so produced may damage DNA, lipid, protein, hamper nutrient absorption, and damage the vital organs. The other health risks that are associated with excess of iron involve disease like cancer, Parkinson's disease, Alzheimer, hepatic fibrosis, and in severe cases may lead to organ failure and even death. So it is very important to monitor the level of iron. WHO has also given the limit of iron in drinking water less than 5.4 micromolar. There are various conventional methods for detection of metal ions that include AAS, ICP-MS, potentiometry, and voltammetry. The main disadvantages of these methods are that they require expensive equipments and trained persons. So we may use naked eye sensor or paper-based sensor for sensing purpose. The main advantage of these methods is that the naked eye sensor provides simple, fast, low cost and high sensitive sensing method, while the paper-based sensor add the portability, disposability and ease of use of the sensor. For this purpose, we have synthesized imine functionalized moiety. So we have taken 2,4-dihydroxybenzaldehyde, dissolved it in DMF using K2CO3 as catalyst. We add propyl bromide to the resulting solution and stir the solution for 24 hours at room temperature. Then the solution was worked up in ice cold water, which result in formation of brown colored PPT. The PPT so obtained were filtered using normal filter paper. Compound 2 so obtained was allowed to react with compound 3, which is amine, and both the compounds were dissolved in ethanol, and resulting solution was allowed to reflux for 5 hours at 78 degrees Celsius. Upon completion of reaction, which was monitored by TLC, the ethanol was evaporated under low pressure, resulting in formation of orange colored compound 4. The compound 4 so produced was characterized by 1H, C13, mass and crystallographic method. As it is clear from the 1H NMR that there is no characteristic aldehyde peak in region from 9 to 10 ppm, showing that it has been completely consumed during the reaction. The peak at 8.95 ppm correspond to the imine proton, and the propyl unit can be represented by peak from 2 to 4 ppm. From the C13 NMR also, we can conclude that as we are not having any peak in region from 180 to 200 ppm, shows that aldehyde been completely consumed during the reaction. And the peak at 156.42 ppm represent the carbon correspond to imine group. The propyl chain can be represented by peak from 56.59 to 78.50 ppm. Then mass spectra show peak at 394.1521 that show the synthesis of our desired product. Crystal of compound 4 were also grown. For this purpose, compound 4 was dissolved in ethanol and was allowed to evaporate under room temperature. Monoclinic crystal system were obtained. The molecule is non-planar with twisted propyl chain. The azo-linked benzene ring were nearly coplanar, and the terminal alkyne show linearity with a bond angle of 180 degree. Figure 2a represents the molecular lattice arrangement of crystal along A axis that show its zigzag arrangement. Figure 2b represents the arrangement of compound 4 in unit cell, which represent 4 molecules per unit cell, and figure 2c represents the packing of molecule 4 along B axis. Then the synthesized compound was used as naked dye sensor. For this purpose, the compound was dissolved in ACN. The ligand solution exhibited a distinct color transition from pale yellow to vivid orange-red upon introduction of iron. No color change was observed with other metal ion that confirm its high selectivity towards iron. So the unique color change enables naked dye detection of iron without need of any instrumentation. The synthesized compound was also used for paper strip testing. For this purpose, we dissolved the compound in ACN and allow the test strip to soak in it. Then the test strips were allowed to dry at room temperature. Upon introduction of iron solution, there was change in color of strips from yellow to orange. As we can see in figure that at 10 to power minus 1 molar concentration of our probe, there was change in color of strip up to 10 to power minus 3 molar concentration of iron. That show that the threshold concentration was 10 to power minus 3 for iron. Then UV visible response of our compound was also recorded. That was recorded in region 200 to 600 nanometer range. 13 different metal ions were used at 10 to power minus 2 molar concentration. Upon addition of iron, new absorption band emerged at 245, 312, 360 and 496 nanometer. The distinct color change from pale yellow to orange red observed that supported by appearance of the new peak at 496 nanometer, which was in visible region. Then titration study was also done. For this purpose, iron at 2 into 10 to power minus 5 molar concentration was gradually titrated into 2 ml solution of our compound, which was prepared in which was prepared in ACN with 10 microliter addition per reading. A progressive increase in peak at 496 nanometer was observed that indicate direct correlation of iron with our synthesized compound. Then LOD was also calculated using linear calibration curve by employing the formula 3 sigma by S, where sigma was standard deviation and S is slope of the curve. The LOD so calculated was 28.71 nanomolar. That confirmed high sensitivity of compound toward iron. Then Bench plot analysis was used to determine the association constant. which was found out to be 2.17 into 10 to power 5 molar inverse. The Joe plot analysis was used to find the stoichiometry between our synthesized compound and the metal ion, which was found out to be 1:1. Then metal interference study confirmed the high selectivity of probe toward iron with no spectral change observed in presence of any other metal ion at 10 to power minus 2 molar concentration. Now in this second section we will discuss about zirconium, that is represented by symbol Zr, is solid at room temperature, is a silvery gray metal with atomic number 40. It is very strong and malleable. The chemical symbol Zr is derived from the name of mineral zircon, which is its primary source. The word zircon itself comes from Arabic word zargan, meaning gold like or as gold. So the name was given due to the golden color of the gemstone zircon. Now we will discuss about application of zirconium and its biocompatibility. Zirconium find extensive use in a wide array of medical, industrial and nuclear application. Zirconium containing compounds have been used in artificial internal organs at a remarkable rate in recent years. Experimental and clinical studies have supported the broad agreement that zirconium compounds are biocompatible and have low toxicity. So although zirconium compounds are low toxic to humans, the specific risks that are associated with zirconium compounds vary depending upon factors such as its chemical form, its concentration, its duration of exposure and route of exposure to our body. Chronic exposure to high concentration of zirconium compounds can lead to adverse health effects including lung leukonoma, carcinogenesis, pneumonitis, skin irritation and pulmonary gluconoma. NIOSH has determined the exposure limit for zirconium compounds, that was 5 mg per meter cube over 8 hours of workday. The short-term exposure limit was determined to be 10 mg per meter cube. So it is very important to determine the level of zirconium in biological system as well as environment. We can use spectroscopic method. The reason for using these method is that they show high selectivity, sensitivity and adaptability to complex sample matrices. In this study, we have used the spectroscopic method, UV visible spectroscopy and the fluorescence spectroscopy. For this purpose, we have synthesized two structural derivatives of triazole. Both these derivatives show some different characteristics while some of the properties were common for both of them. For example, the orthotriazole show UV visible and fluorescence response towards zirconium, while both para and ortho isomers show antioxidant activity, anti-cancer activity and molecular docking analysis. Here we have given the synthetic route for probe 8A and 8B, which are structural isomers that are ortho and para triazoles. So for this purpose, we have taken the hydrazine moiety, reacted it with vetraldehyde using ethanol as solvent and refluxing the solution for 5 hours result in formation of Schiff base 3. The resulting Schiff base was allowed to react with dry bromoethane to form the bromo derivative. Then this bromo derivative was allowed to react with sodium azide using DMF as solvent, refluxing the solution for 5 hours at 90 degrees Celsius result in formation of the azide derivative 5. The azide derivative so produced was allowed to react with ortho and para alkyne derivative in presence of copper catalyst and T and THF in 1:1 ratio, refluxing the solution at 60 degrees Celsius for 5 hours resulting in formation of compound 8A and 8B. All the synthesized compounds were characterized by 1H-C13 mass and crystallographic method. So compound 4, which is our bromo derivative, was light yellow solid. The 1H NMR observation of compound 4 show that new ethyl chain give two distinct peak at 3.4 and 3.8 ppm. Each peak correspond to 2 protons. C13 NMR show that bromo-ethyl chain give peak at 28.36 and 51.96 ppm. The mass spectra give peak at 422.94 that also show the synthesis of our bromo derivative. Then azide derivative, which is represented by compound 5, was pale yellow solid and was obtained in 75% yield. The 1H NMR of compound 5 show that there was two distinct peak in region from 3.36 to 3.50 ppm, and each peak correspond to 2 protons. The C13 NMR showed that the azido-ethyl chain showed peak at 48.38 and 49.41 ppm. The peak at 403.24 in mass spectra also confirmed the azide derivative synthesis. Then compound 8A was off-white solid, was obtained in 90% yield, and in 1H NMR, after cyclization of the triazole ring, the CH proton appeared at 7.1 ppm. This OCH2 group that represent the propagyl chain give peak at 5.25 ppm, and aldehyde protons appeared at 10.38 ppm. Aromatic proton give well resolved peak in region from 6.8 to 8 ppm. The C13 NMR show that triazole carbon give peak at 121.33 ppm. Propagyl carbon that was next to oxygen atom give peak at 62.45 ppm, and aldehyde carbon showed peak at 189 ppm. The mass spectra also confirmed the synthesis of our desired product, which is orthoderivative triazole. Compound 8B that give off-white solid and was obtained in 92% yield. The 1H NMR showed that triazole CH proton appeared at 7.11 ppm. OCH2 group of propagyl chain appear at 5.21 ppm, and the aldehyde proton could be seen at 9.88 ppm. Then the C13 NMR show that triazole carbon can be represented by peak at 124.69 ppm. Propagyl carbon that was next to oxygen appeared at 65.84 ppm, and aldehyde carbon give peak at 190.78 ppm. The mass spectra also confirmed the synthesis of our para derivative. Then the crystals of all these compounds were also obtained. For compound 4 and 5, both of them were dissolved in dry ether and under slow evaporation at ambient temperature result in formation of crystal of both the compounds. Compound 8B was dissolved in ethanol, and same slow evaporation method was applied for crystals. Then preliminary UV visible analysis of 8A and 8B was also done. 8A show peak at 554 nanometer, 311 nanometer, while 8B showed peak at 274 and 311 nanometer. These peak correspond to pi to pi star and n to pi star transitions. That was due to heteroatoms and conjugated pi electron system in these compounds. Then the selectivity by UV visible response of ligand 8A towards zirconium was also recorded. Only zirconium caused a significant change in the spectra upon 10 microliter addition to our synthesized ligand. The spectral change that was observed was peak at 254 nanometer diminished. The new peak at 275 nanometer appeared, and there was hypochromic shift at 311 nanometer. This may be explained on the basis of HSAB principle and host-guest fit relationship. As the ligand, that is a hard base, as it contains nitrogen and oxygen, which are small in size and contain lone pair of electrons. These bind with zirconium, which act as hard acid in this case, so they show strong binding. The host-guest fit relationship show that zirconium matches the ligand cavity size and hence enhance the selectivity. Titration study of ligand 8A towards zirconium was also studied. Ligand was taken at 10 to power minus 6 molar concentration, and for zirconium we prepared 10 to power minus 4 molar concentration. There was gradual decrease in peak at 254 nanometer, and the band at 311 nanometer undergo a hypochromic shift. LOD was determined using linear calibration curve, which was found out to be 50 nanomolar. Then association constant was determined using BH plot method, and the association constant was found out to be 0.506 into 10 to power 7 molar inverse. The binding stoichiometry between the synthesized ligand and the zirconium ion was also determined using Joe plot analysis method. Equimolar solution of our synthesized ligand 8A and zirconium was dissolved in methanol, and the volume was taken to be constant at 2 ml per vial, and the inflection point at 0.5 mole, that showed 1:1 binding between both of them. Interference study was used to show the selectivity of ligand towards zirconium and the minimal spectral change from other metal ion that show a strong selective response only in case of zirconium. Fluorescence sensing study was also done with zirconium by ligand 8A. For this purpose, ligand 8A was dissolved in methanol that showed a emission band at 400 nanometer under excitation wavelength at 320 nanometer. There was no significant change with other metal ions, while in case of zirconium, there was a significant fluorescence enhancement. This indicates the specific interaction and high selectivity towards zirconium. Then fluorescence titration of ligand 8A with zirconium was also done. For this, there was a gradual increase in zirconium concentration from 10 microliter to 140 microliter, which was prepared at 10 to power minus 7 molar concentration. In this experiment, the ligand was prepared at 10 to power minus 8 molar concentration. There was weak fluorescence without metal ion, which may be explained on the basis of intramolecular charge transfer and CN isomerization. Upon introduction of metal ion, there was chelation enhanced enfluorescence that affect and reduces the ICT and isomerization, and hence the emission band boosted up. The linear calibration curve was used to find the limit of detection, that was found out to be 0.9 nanomolar. Now coming to third section, here we will discuss about nickel element. So nickel, that is represented by symbol Ni in periodic table, has atomic weight 58.693. The chemical symbol Ni for nickel was derived from German term which is Kupfernickel, which translate to false copper or Abel's copper. The German miners use this term to describe a copper-like ore that yield no copper when proceeded, leading to the belief that it was trick played by the devil. So nickel is an essential trace element for living system and crucial in several industrial applications.